In this video, we'll be demonstrating how to do many of the calculations that we discussed during the ANOVA lecture in R. One preparation piece for this video, I've gone ahead and typed in all of the data from the notes as we'll be working through the examples that were in our notes in this R session. You may choose to do the same thing. You can also, if you prefer, just pause the video after I've copied and pasted it in, and then you could just copy it down by hand if you prefer. What I did is I took the values from the notes in R, I pasted them into Excel as a table, then I saved that Excel file as a CSV, and then wrote the CSV. So that's how I did this quickly, and you're welcome to do the same thing. I know we've already talked about copying and pasting stuff into Excel, and then importing Excel stuff or CSV stuff into R, so I'm not going to revisit that here, but you're welcome to do so if you want to. That said, we will talk a little bit about managing data once it's in R if we want to manage it in R as opposed to in Excel or other places. So for the first example, we had 3 cities. We were looking at the number of hours per week that managers worked within each of 3 plants in 3 different cities, Buffalo, Pittsburgh, and Detroit. I'm going to go on and make a data set, or this data frame, with the data from Buffalo, Pittsburgh, and Detroit. And then really quickly, I can use this apply command to quickly calculate the column means, and I'll just paste that to also calculate the column variances, which were provided in the example in the notes, so we can just see and double check this really quickly if we wanted to. If you want more information about the apply command, you can do question mark and then apply to get more information about that. So in R, if I look at my data real quick, DAT, you'll see that this is written in that wide format where I have the different levels of my factor written as the column labels and not as its own column with maybe city as the factor and then Buffalo, Pittsburgh, and Detroit entered at the appropriate places in different rows. So in R, when we perform an ANOVA, we really prefer the long data format to the wide data format. Wide is useful for doing it by hand, so if I had to calculate out each of these values, you see I can do that pretty quickly in R. It's not too bad. But to get to long format, or to do the analysis in R, we prefer the long format. And so we'll discuss how to quickly get to long format in one of the ways. I'm going to be using the package tidyr for this next command. It's a pretty useful package that has a lot of different features, and in this particular case it's going to give us access to a command called gather, a function called gather. So again, there's lots of ways to do this. This is just one of them. I'm going to call my long data set LDAT, and then I'm going to use the gather command. Now, because all of my data is in this wide format, I don't need to do anything else with it, then I can use gather in a pretty simple way. I'm going to give it the name of my wide data set, and R is going to turn this into a long data set. Again, it's going to make the column names into its own column. So I have to tell it, what do I want to name the new column, the column of these different levels? And I'm going to name the new column city. That is, what is the factor name for each of these different levels in the wide data? And I'm going to call that factor name city. The last thing I need to tell it is, okay, well, what are these individual numbers called? Like, what is the variable that these individual numbers are? And remember, these were hours per week. I'm just going to call hours. And if I run that command and then look at what my long data looks like, I can now see that under the city, I have Buffalo, and then hours 48, Buffalo hours 54, etc. Pittsburgh hours 73, Pittsburgh hours 63, etc. and Detroit hours 51, Detroit hours 63, etc. So this is my long data format that I'm going to want to use for when I'm running my ANOVA. Interestingly, it's really easy to spread it back out. Like if I had long data and I wanted to go to wide data, all I would need is an ID column. So I could do maybe to spread it out, I'll make a separate data set for this. And this is just going to be my LDAT data, but then I'm going to add an ID column. And you don't have to worry about these commands. All I'm doing is creating an ID column that's 1 to 5, and we can look at this. Excuse me, I mistyped something. Rep equals 3. So we can look at what I'm doing here. Pretty much what I'm saying is that for within each city, the IDs are 1 to 5. So this is employee number 1, employee number 2, number 3, number 4, number 5 in Buffalo. And then this 6th entry is employee number 1 from Pittsburgh, employee number 2, number 3, number 4, number 5. And then this 11th entry is employee number 1 for Detroit, etc. I need the IDs to tell R which order should they go in when I'm putting this back into wide format. So that's where the IDs come from. They'll now go in the order 1, 2, 3, 4, 5. To spread this back out, I use the spread command instead of the gather, and I'm going to use this toSpread_dat dataset that I made with the ID. And now I just give it the same information. What column do I want to be the row names? So I want this column of cities to now be, the column names, Buffalo, Pitt, and Detroit. And what variable do I want to be the entries in those columns? And I want the hours to be the entries in those columns. And you'll see that this spreads it back out just like we had earlier, except with that ID variable as well. Typically, you end up getting data in wide format and entering it that way and then gathering it to make it long format for analysis. In my experience, it's not too common to spread it back out, but it's good to know the command in case you're interested or ever need to. All right, well now it's time to fit the ANOVA model. So we're going to fit the analysis of variance and use the AOV command for an analysis of variance. My Y variable, my outcome, is hours, and I want to see, does the city or the different plants in the different cities affect the hours? So I have my dependent variable, and then a little squiggle, and then my independent variable, or the outcome variable, my squiggle, and then my factor, what I believe is affecting the hours. I'm going to give it my data set name, and then I'm going to ask for a summary of this model. If I just look at mod by itself, the AOV, it's called an object, but the AOV output raw saved, it doesn't look very pretty. When I ask for the summary of the model, this is what gets me what looks more like my traditional ANOVA table, just without the total column, which is fine because I can always find it by adding up the degrees of freedom and the sums of squares. And remember, in the total column, we didn't do mean squares or F values or P values. A student asked previously in class in their journal why I work so often in class when we're doing things by hand with critical values, and I don't work as much with p-values. And the honest answer is p-values are a pain to calculate without computers, but critical values are really easy to use by hand. On the other hand, when I work in the computer, I never ever use critical values, and I only use p-values. The reason being is when I run an analysis of variance in R, I have the p-value already printed out for me. It's really, really, really handy. And actually, I have a little star system that tells me my p-value, 2 stars, is between 0.001 and 0.01. In this case, using a traditional cutoff of alpha equals 0.05, my p-value is less than alpha, and I reject the null hypothesis. And this is actually how I interpret my results. And frankly, when I'm working with this on a computer, again, I never really look at critical values. I only look at the p-values of an analysis that I ran. You can also double check that all of these sums of squares, the mean squares, the f-value, the p-value, and the degrees of freedom line up with what we saw when we ran this in our notes. For the post hoc test to take advantage of the Fisher's LSD, what I'm going to need is a new library. So I'll load up this package called Desk Tools with a capital D, D-E-S-C, and a capital T, T-O-O-L-S. If you haven't already installed the package Desk Tools, don't forget that on every computer you have to make sure you install that package. So install.packages, capital D, Desk, D-E-S-C, capital T, T-O-O-L-S. And then don't forget to do your library command to load up all the functions that it has available. One of these that we'll be using for our post hoc test is called post hoc test, capital P, capital H, capital T. And I just give it my ANOVA model and tell it which method I want to do. Now, we didn't talk about any other methods in class. We just talked about the Tukey's LSD. So I'll give it LSD. I'll note, and this is typical of software, it doesn't actually give me the least significant difference. What it does give me is the pairwise comparisons and the p-values for each of those pairwise comparisons so that I can check if each of the pairwise comparisons are themselves significant. I see there's no statistically significant difference between Detroit and Buffalo, but I do see that Pittsburgh to Buffalo and Pittsburgh to Detroit are both statistically significantly different. If I've already forgotten which side is higher and which side is lower, it's kind of nice because it tells you the direction of the subtraction within this output. So Pitt minus Buffalo is a positive number, positive 13 is the absolute difference. So, excuse me, positive 13 is the directional difference. So it could be a negative if it were the opposite way. And because this is a positive number, that means Pitt is bigger than Buffalo. If you've forgotten, you can always go back up to your wide format, run that apply, and find the mean values for each of the columns. We see Pitt, 68 hours, is on average bigger than Buffalo's 55. From our post hoc method, we see that this difference is statistically significant, both from the p-value and because the confidence interval of the difference is not including 0. The confidence interval of the difference is pretty handy because this says what's a reasonable range of hours that the difference could be. In this case, the difference could be anywhere between 6 and 20 hours. All of those are reasonable conclusions. 0, however, is not within this interval, and so I wouldn't consider 0 to be a reasonable conclusion given this data. All right, let's move on to our factorial ANOVA. So again, I already have this data typed in. You're welcome to go on and type it in now if you want to, or again, you can pull it and copy it from the notes directly so you don't have to type all that. Either way is fine. I'm going to call this data set facdat, and it's just going to be the data frame of industry and then my different cities, Cincinnati, Cleveland, and Columbus? I think it's Columbus. All right. Now, just like before, I can use these apply commands. Apply facdat to mean. But you'll notice that it's going to give me an error in this particular case because industry is not a number. So I can't really calculate the average industry. In this case, what I can do is use my square brackets. This is what allows me to select individual rows or columns, and I can use a minus sign. So remember, the second entry in a square bracket, it goes rows then columns when I'm dealing with a data frame. So if I did 1, this would select the first column. If I did -1, this would take out the first column in the second entry after the comma. Remember, when we do no entries, it pulls everything from that. So this is saying all the rows and everything but the first column. The little number 2 means for each column, calculate the mean. And I could quickly do the variance for each of the cities as well. The trick, though, with this particular problem was that it wasn't just city as factor. We also had industry as a factor, and it's not as easy to calculate the means and variances for the industry using this format because industry is listed as a column. So what I have to do is again reorganize my data. I'll call this fac LDAT for a long data, and again I'm going to use the gather command. Now real quick, if I just use gather factdat, and I want to gather my different columns as city, the entries, I believe these were salaries or wages for individuals. If I just ran this, R is going to think that every column of this data set, industry, Cincinnati, Cleveland, and Columbus, are all city names. But in truth, industry isn't a city name. Industry is itself a factor. So I don't want it to do industry. I just want it to do Cincinnati through Columbus. So in this case, I can tell R which columns I want it to do. And I'm going to do Cincy, Columb. And this tells R I want you to do Cincinnati through Columbus and nothing else. Looking at the data that I have now, I can see that this has been arranged in long format, where instead of cities being column names, now city is itself a column with entries for each city and the wages provided. Incidentally, similar to apply, when we have data in long format, we can use the aggregate command. So for instance, let's say I wanted to aggregate my wage based on industry. Wage is the outcome, industry is the input for fac LDAT, and I wanted it to calculate the mean. Then I could break down the mean and the variance for industry. Again, you don't have to use this. Oh, excuse me, var is the command. You don't have to use this, but if you wanted to, you are welcome to. Now, how do I construct a two-way ANOVA with interaction in R? Well, I'll call this my fac mod, and again, I'm going to use that AOV, or analysis of variance command. Now, wage is my outcome, and my two independent variables are now city, which city did the individual work in, and industry, what industry do they work in? So I have city and industry. I can use a plus sign to have R add city and industry as two independent variables without an interaction. If I want R to add it with an interaction, I use the little star or multiply them together. And my data in this case is going to be fac LDAT. Similar to the above, I'm going to use the summary for fac mod to look at my results. And we see that my results match exactly to what I had previously. Actually, you'll note, I think the order is backwards. I think in my notes I had industry first, then city. Here I have city first, then industry. If I change the order in the equation, they would display differently. But you'll note that this doesn't actually affect the numerical output that I'm seeing in this particular form. Interpreting this output, I see that city is a statistically significant factor and its effect on wage. Industry is not a statistically significant factor, though it's pretty close. And the interaction is not statistically significant. That is, the effect of industry on wage doesn't depend on what city you're in, and vice versa. The effect of city on wage doesn't depend on the industry. All right, so for the last thing, let's talk about blocking. So again, I'm going to copy and paste my information from the problem. Now, one thing you'll note that might not happen if you just read in the data is that automobile, I'm putting the number of the automobile in quotes. This stood for vehicle 1, vehicle 2, vehicle 3, vehicle 4, vehicle 5. Well, for R is going to think, if you just put in the numbers, that the numbers actually mean something. Like vehicle 2 is twice as good as vehicle 1, and vehicle 3 is 3 times as good as vehicle 1, or something like that. But here, we're actually using the numbers as kind of the name of the car. This car's name is vehicle 1. This car's name is vehicle 2. So when I do that, I have to make sure that I put the numbers in quotes so that R doesn't get confused. It really comes down to, do I want R to look at this as a number or a name? And for these, automobile 1, automobile 2, automobile 3, automobile 4, and automobile 5, I want R to look at them as a name, not a number. Go on and clear my screen here. All right, now let's look at blockdat. So I'll make this a data frame with automobile, blend X, blend Y, and blend Z. Some of you may ask, why do I type it in wide format, excuse me, and then change it to long format? One of the reasons is, well, the first reason is I'm typing it in how it's presented in the problem. The second reason I do it this way is because it's actually really common to get data in this wide format. It does tend to be a little easier to type in sometimes. The problem comes when we try to do an analysis with it and it doesn't really end up working out. So it's pretty common to have to do this transformation, transforming from the wide data to long data. So in this problem, I'll create block LDAT, and again, I'm going to use this gather command. And again, I have a column that is not one of the blends of gasoline. So I'm going to need to tell R exactly which columns are the blends of gasoline. I'll note real quick, the reason I can use gather without loading the library every time is the library sticks around for the whole R session. So it'll stick around until I close R again. Now, if I open R back up and try to start at this line, I'll get some somewhat cryptic command or error message that R can't find the gather function. And that'll just remind me that I have to go up and run that library command before I can run the gather function for that R session when I reopen it. Using the gather command, I give it my data. I give it the name of the factor, which the levels are the column names. So the levels are blend X, blend Y, and blend Z. The factor is, I'm just going to call it blend. And what's the output here? Well, the numbers are each representing the miles per gallon. And then again, I have to, because automobile isn't a blend, automobile is its own thing, I have to tell R, well, what columns are the blends? And it's really easy here, because I named them nicely. This is blend X through blend Z. And I can look at my block LDAT and see that this read in nicely. When my data is typed in like this, and I can easily copy and paste it from my notes into R, I don't tend to take the time to retype it by hand. The other reason is because if I'm doing this, this line is so much easier to type than retyping all of this information by hand in the long format. So why would I type it in by hand if I really don't have to? To create our block model, again, we're going to use the AOV command, analysis of variance. Our outcome is miles per gallon. That's what we're studying. Our independent variable that we care about is the blend. And the blocking factor is the automobile. Notice and recall that within blocking factors, I don't look at the interaction term between the two independent variables. I just let the blend and automobile go in without an interaction term. And in R, as we talked about before, we do that with the plus sign. Data equals block LDAT. The other thing to remember as I'm writing this out is that when I look at my model, I'm not looking at the significance test for automobile. That's not something that we're testing here because that's our blocking factor. What I'm looking at is the significance test of blend. Now you'll see in our notes we didn't display the F value or the P value for the blocking factor because we knew it was a blocking factor. But in R doesn't really know. We just told R it's a variable. And again, the analysis is the same. It's the interpretation that changes. So the F value and P value of automobile, our blocking factor, aren't really interpretable, and mentally we should ignore them. We know this because in our design, automobile was treated as the blocking factor. Blend, however, was our variable of interest. So looking at blend, I can interpret this significance test. And here it's 0.0689, which is greater than 0.05. So classical wisdom would say we fail to reject the null hypothesis. We don't have enough evidence to determine that there was a difference in blends. In reality, though, again, as I've mentioned in the lecture videos, this is pretty close to 0.05, and we only did 5 replications or 5 blocks. So in this case, I might come back to my boss or client and tell them that, hey, the value's pretty close to p equals 0.05. We may get some more data to figure out if one of the blends is actually better. If I wanted to figure out where the differences in the blends are, if it was a statistically significant ANOVA, I could run the Tukey's LSD for the different blends to figure out where the differences lie. Now, I will say that pairwise post hoc comparisons are a little bit more difficult when we have another variable involved in a factorial ANOVA, and we're not going to cover that in this class. But the idea is pretty similar. We look at the pairwise comparisons of all the blends. We would just want to account for the impact of automobile when we look at all of those pairwise comparisons. This has been a presentation on how we can implement the analysis of variance, or ANOVA, utilizing the R software.